I'm going to give you a brief overview of what we learned in lessons 10 through 17 to help prepare you for the Unit 2 test. Okay, so the first thing we're starting with is Lesson 10, which was the first part of probability. Okay, in Lesson 10, the first thing we started with was Venn diagrams and two-way tables. So I'm just going to talk about Venn diagrams for a moment. Okay, and remember there's basically two types of Venn diagrams. Venn diagrams that have no overlap versus those that have overlap. And we have special terms for these when they happen. No overlap we call mutually exclusive. And when they do have overlap, we call that not mutually exclusive. And remember what this really means is that if two events are mutually exclusive, that means they cannot occur at the same time. Okay? Whereas if they are not mutually exclusive, that means they can occur at the same time. Okay, some examples of this are example of mutually exclusive events are things like do you have kids or not? Either you do or you don't. Those are really things that are mutually exclusive. Okay, so a few examples of that are you're either alive or you're dead. You're either pregnant or you're not. Okay, you either took the bus to work or you took the car. Okay, now certainly that last one is a little oversimplistic because it's quite possible you drive to the bus station and then take the bus. But I just mean if you're only using one mode of transportation. Okay, things that are not mutually exclusive, things that can happen at the same time. Some examples of this are if you have a cat or a dog, it's possible that you have both. Okay, wine or beer, it's possible to drink both. Okay. Salad or pizza. Okay, again, oversimplistic examples, but hopefully you get the point. All right, and what those look like in their Venn diagram is that if we have things with no overlap, and no overlap in the circles is what I'm talking about, okay, and these have overlap of the circles in the Venn diagrams. So let's look at an example of that. Okay, so let's say I've got a Venn diagram here, and I'm talking about what sport you play. Okay, and I'm totally making this up, so this might not be founded in fact, but let's just suppose that you either play softball or baseball. You can't play both. Okay. And let's say I've got a 3 here, a 5 here, and a 4 here. Okay, notice there's no overlap. So I'm telling you, you can either play baseball or softball. Okay, so just a few reminders about what this Venn diagram means. Okay, so everyone in this Venn diagram plays a sport of some kind. Okay, and the number of people represented, to find that, we add up all the numbers we see. And that means we're adding the 3 plus the 5 plus the 4. So we have 12 people total represented here. Okay. Now this 3 here, that is someone who plays a sport, but it's not softball and it's not baseball. Okay. Now this 5 here means these are all the people who play softball, and the 4 is all the people who only play baseball. Okay, so now I can find some probabilities using this Venn diagram. So here's some example probabilities. I could find the probability that someone plays softball or baseball. Okay, so what that or entails is either one, and that's what we call an inclusive or. Okay, so what we're looking at here for this one is the people who are in the softball circle and also the people in the baseball circle. So how we calculate this then is we look at the number of people within the softball circle and the baseball circle is with the or, we're not caring which circle they're in. We just want to know if they are in one of these two circles. And that's what that or really entails. Okay, so to find this probability, we're going to take the 5 plus 4 and then divide it by the total. And our total here is 12. Okay, so to calculate that, in the top, what I put is the number of people in either circle, and I divided it by the total number of people represented. Okay, and then of course, to figure this out correctly, we've got to put this in our calculator. This is 9 over 12 and 9 over, okay, so the probability is 0.75. Okay, so remember, the probability is always going to be that decimal. We use the fraction to get the decimal. The answer is the actual decimal. Okay, we can also find the probability of softball and baseball. Okay, and the and is a little bit different. What the and means is this means they've got to be in both of those circles. Okay, so that and, we're looking at really the overlap. Okay, because in order to be in both circles, there has to be some kind of overlap. But in this example, we don't have any overlap. Okay, so the probability of this happening is 0 out of 12. Because there's no people, there's no overlap. And that's 0. And in fact, this probability, this particular probability equaling 0 is what tells us it is mutually exclusive. Or these two things are mutually exclusive. So we use this as a check. So if you're wanting to determine if two items are mutually exclusive, all you've got to do is find out how many people are in both of those categories. And if that value is 0, that tells you they are mutually exclusive. Okay, let's switch now and let's talk about this other option, this not mutually exclusive, the Venn diagrams that do have overlap. Okay, here's an example. Let's look at pets. And let's look at one circle of cat owners and another circle of dog owners. Okay, and so let's suppose I've got 19 people down here, 5, 2, and 10. Okay, so there's my Venn diagram of pet owners. And just a reminder, what this means, everybody in this cat circle has a cat. That's why we're looking at this circle here. That means they have a cat. And then everybody inside this dog circle has a dog. Now, these people down here in the corner, this 19 here, those are pet owners because everybody inside this box owns a pet. But this 19 just means they do not have a cat or a dog. They have a different kind of pet. We don't know what kind of pet it is because that type of pet isn't represented. We just know it is not a dog and it is not a cat. Okay, so now if we wanted to, let's find those same probabilities that we did before. Let's find the probability of owning a cat or a dog. Okay, again, what we're looking for here is this means either one. Okay, and what's nice is that since we have this Venn diagram, this makes it a little bit easier than if we were to have a table. Okay, we don't really need a formula or anything. We can just use our Venn diagram. We're looking for anyone who's in either the dog circle or in the cat circle. Okay, so we're talking about these 5 people here, these 2 people here, and these 10 people here. So that's 5 plus 2 plus 10 out of that total. And we haven't figured out the total yet, but we can figure that out real quick. That's going to be every number included. 19 plus 5 plus 2 plus 10. So that's 17 plus 19. That's 36. So my probability of owning a dog or a cat is 5 plus 2 plus 10 all over 36. So that's 17 out of 36, which when we figure out that fraction, 0.472. All right, what about the and? What about the probability of owning a cat and a dog? Okay, and just like before, what this and means is we're looking for the overlap. And if we look back at our circle, these are the people that are in both circles. They own a cat and they own a dog. And do you see where that overlap is? That's right here. So I've got 2 people in that category. So that's 2 out of 36, 0.056. Now, notice the and is not 0. Okay, so this right here, this not being 0, tells me that these 2 events are not mutually exclusive. So I know that owning a cat and a dog are not mutually exclusive. Or put another way, that means you can own a cat and a dog simultaneously. So that's the basics of the Venn diagrams. In lesson 11, we're going to take Venn diagrams and this probability and make it a little more complicated. But I'm just sticking to the lessons just to help you organize and know where to find what you're looking for. Okay. So let's go to the second thing we discussed in lesson 10. The second thing we discussed in lesson 10 was independent versus dependent. So independent events are events where the outcome of one event has no bearing whatsoever on the outcome of another event. Okay, so some examples of this are some popular examples that people refer to often are flipping a coin or rolling a dice. Getting heads or tails in your first flip has no bearing on what your next flip probability is going to be. Rolling a dice has no bearing on what the probability of what you're going to get for the second time you roll the dice. Those are completely separate events. Okay? They have nothing to do with each other. They're totally independent of each other. If you get heads 6 times in a row, that doesn't change the probability of you getting heads the 7th time. Okay? And dependent events are events that are not independent. So these are events where the outcome of one event does impact the outcome, the probability of something, whatever happens next. Okay, so one really popular example, and the way to think that I like to think about this the most, is playing poker or playing any kind of card game. Hey, if we're playing blackjack and I get an ace, that changes your probability of getting an ace, right? Or if we're playing, well, really even Go Fish, right? If I have an ace or 2, any card that you know I have changes the probability of you getting that same card. Okay, so that's a dependent event. Okay, and in order to verify if something is independent or dependent, is we need a conditional probability. And the conditional probability is in lesson 11. So with that, let's go on to lesson 11. Okay, so this is probability part 2. The first thing we learned in this was those conditional probabilities I had just mentioned. Before we talk about how we use conditional probabilities to determine if events are independent or dependent, let's first just learn and remind ourselves what a conditional probability is. The way I like to think about it is I like to think about the conditional probabilities as introducing a caveat to the probability. So you're not talking about the whole group anymore. If you have a conditional probability, you're just talking about one aspect, one of the groups in the greater picture. Okay? Okay, so the biggest thing that this changes then when we're finding that probability is our denominator, that bottom number now is no longer going to be everybody. It's going to be only the people in the group for which we're interested in. Okay, so for example, let's look at how we write these conditional probabilities, because this denominator changing is really written into the notation if you think about it the same way I do. Okay, so here's our conditional probability. This is what that looks like. Okay, so this is how we say this. This means the probability of A given B. That's how we say, that's technically how we say that. Okay, That's the technical definition. And this vertical line here, that's the given part. Okay, the way I like to think about it, I like to think about it slightly differently. Let's change these arrows. Okay, my way is, I like to think about it as saying, of all the people in this B category, how many of them satisfy A? Okay, to me, that makes more sense, but I know for some of you that first thing makes more sense. So, choose which one makes more sense to you and the way your brain works and just roll with that one. Okay, now that's what it means. So how do we figure it out? This B, remember how I said that the conditional probability is a caveat and it changes the denominator. Okay, if we were finding the probability of just A, that's going to be the number of people who in A divided by the total. But this is different for the conditional probability because now we're not talking about everybody anymore. Probability of A given B. Now, this is the new denominator is the B, just the number of people in B. Okay, and so what I like to think of is I like to think of this vertical line as a way to indicate my denominator is changing. Because if you take this and you flip it sideways, you see here is my new fraction bar. The B goes on the bottom, and on the top what I'm going to put is the number of people in A. Okay, but of the people in B, so just looking at B, how many of them are also in A? Okay, formally, how we say this is this new top is the probability of A and B. And our bottom value is the number of people in B. Okay, I find this a little more confusing. I personally like to think about it this first way. Okay, I think it's more intuitive. But again, like the other things, you think about it and you write it down the way that makes the most sense for you. Okay, let's look at an example because that always clarifies things a little bit more. Okay, so let's go back to the cat and dog example actually on this last page. Okay, so I've got my cats and dogs. I've got the dogs are here and I've got the cats. Cats are here. If I wanted to find the probability of someone owning a cat, given that they have a dog. Okay, so this probability now, I'm not talking about everybody. I'm just talking about the people that own a dog, which tells me that I'm not looking at the total anymore. I'm only looking at the people here. Okay, so my fraction is going to be the total number of people who own a dog is going to be the denominator. Okay, and my top number is going to be the number of cat owners within that circle, only people in this circle here. Okay, so when I'm working on this problem, what's happening is I'm ignoring everything else. All of this is getting ignored. Let's do something bigger. Okay, I'm ignoring this. My world is only that dog. Okay, so of everybody in my world right now, of just the dog owners, how many of them, oh dear, how many of them own a cat? Okay, and you see, that's this 2. That's this 2 right here, because that 2 is from that other circle. Okay, but I didn't erase them because they're in that red circle. So this then, the fraction I'm looking at is 2 over 12. So you see my denominator changes. My denominator is 12 because I only have 12 dog owners. Whereas total, our denominators up above, we're looking at 36 people. So this is 0.167. All right. Now, if we were to look at the probability of just owning a cat, and maybe we should have done that one first, but what are you going to do? Okay. Now, the probability of owning a cat, I'm talking about everybody now because you see, I don't have that caveat, that vertical line. Remember, this vertical line is what tells you that denominator is changing. Okay, and that's how I think about that vertical line. That denominator, it becomes my fraction bar and tells me the number down below is not everybody anymore. It's just the people who come next. Okay, so the fact that this doesn't have that vertical line tells me I need to get rid of that, and now I'm talking about everybody. Okay, so this is the people who own a cat out of everybody. So I'm looking at everybody in this circle here, out of everybody, out of the total. How many people own a cat? That's out of the total. Okay, so to figure this out, I do need to look at everybody here. Okay, so you see this 2 here. Oh, you can't see that. You can't see me. Okay, so here, this 2 here, when I'm figuring out the probability of cat, I'm thinking about everybody that's in this blue circle. I don't care that that 2 is also in the red circle with the dog. All I care about is how many people are in this blue circle. And that's the 5 plus a 2. So that's 7. Whoops. 5 plus 2. There you go. I know you can do this math easily. I'm just writing it down to show you where I'm getting these numbers from. Okay. And that's out of the total number of people represented. What was that? 30 something. Okay. So that's 5 plus 2 over 36. So that's 7 over 36. 0.194. Okay, so you see this is a pretty big difference. Well, actually, not that huge. 16.7% versus 19.4%. That's pretty similar, actually. Excuse me, but the fact that these 2 are not exactly the same values means that these 2 things, owning a cat and owning a dog, are not independent. So that's what I get from these here. This tells me, okay, so because the probability of owning a cat and the probability of owning a cat, given that you already own a dog, because these 2 probabilities are not the same, I know that these 2 events are dependent. They are not independent, they are dependent. Okay, so what that means is owning a dog does influence whether or not you own a cat. Okay, so another way to think about this with determining that independence and dependence is, what we did is we changed the denominator. Right here with the probability of cat, we're looking out of everybody, what's the probability you own a cat? Versus out of just dog owners, what's the probability you own a cat? So we changed the denominator, and that changed the probability. Changing the denominator changes the probability, which is what tells us they are not independent. If these 2 events were independent, changing the denominator would not change the probability. So let's summarize this. In order for 2 events to be independent, changing the denominator cannot change the probability, or should not. Okay, so what that means is that if 2 events are independent, just to summarize and put it formally, if two events are independent, that means the probability of A is going to equal the probability of A given B. Okay, and you see this denominator is different because here, with the probability of A, my denominator is the total. This is out of the total, whereas here, the probability of A given B, the probability is out of just B. So if these 2 things are not equal, then that means the 2 events are dependent. Okay, and what this means, just to summarize here, if they are dependent, B changes the outcome. Okay, you can also think of it as B has an effect on A. Okay, so that's lessons 11 and 10. Let's go forward then to the next lesson, lesson 13. Excuse me, lesson 12. 12 comes after 11. Yes. Okay, so in lesson 12, we're starting a really different thing. Okay, so lessons 10 and 11 are related. 12, we're changing gears completely. Okay, in lesson 12, we're figuring out discrete probability distributions. Okay, and this is Discrete probability distributions, remember, are looking at discrete variables. These are distributions of discrete variables. And remember, discrete variables are basically things you're counting, okay? And we always start with 0 because it is possible to have nothing of what you're counting. 1, 2, 3, 4, etc. Okay, and because we're counting, you either have 1 or you have 2, and that's where the term discrete comes from. There's nothing in between 1 or 2. If you have more than 3, then that means you have 4 or more. If you have less than 3, you've got 2 or fewer, 2 or less. Okay, discrete means counting, like on your fingers. Okay, some examples of discrete variables are number of eggs or clothing size, right? I don't know about you, but I'm often in between sizes. You either have medium or you have large. There's no medium and a half. Your shoe size options are either 8.5 or it's 9. You can't do 8 3/4. Those are also discrete variables, okay? Or the number of cars in a parking lot, etc. And the probability distribution looks like a histogram, except the difference is there's a gap between the bars. That's really the biggest difference between the two types of histograms we do. If it's discrete variables, there's a gap between the bars to indicate there's nothing occurring in between these. Okay, so it looks like this, where I've got 0, 1, 2, 3, 4, 5. Okay, so there's an example of a discrete probability distribution. Okay, and remember we could also have a frequency table. All right, and we often see frequency tables. And one thing that's important to keep in mind is that the relative frequency is the probability. Okay, so if I were to put probabilities on top of these, and I'm just going to make some numbers up. All right, so here's my probability distribution. That tells me that the probability of getting a 3 is 0.2 because the relative frequency of a 3 is 20%, which means that probability is 0.2. Okay, so with this type of discrete probability distribution, I would give you some values, and I might have you fill out a relative frequency distribution table. Okay, or I might give you something that looks like this probability distribution here. Remember, if we have a frequency distribution table, that's the value that would look like this, where I'd have those 3 columns. I'd have the value, the frequency, and the relative frequency. Okay, where I would have 0, 1, 2, 3, 4, and 5. The relative frequency would be the values here in blue. So 0.05, 0.10, 0.15, 0.20, 0.25, and 0.25. Okay, so then the relative frequency, let's say I had 10 items or 100 items, then 5 of them are in this category, 10 in this category, 15 in this category, 20 in this category, 25 here, and 25 here, for a total of 100. And then so these relative frequencies here in this column are the probability. So I can look at it 2 different ways. I can look at it using this column, or I can look at it using the distribution, the probability distribution. Okay, at the end of lesson 12, we started looking at the binomial distribution. In the interest of your sanity, I'm going to do it all under lesson 13, okay? But just know that it started at the end of lesson 12, and I'll make a note of that in a moment. Okay, unlike lessons 10 and 11, where there was kind of really different stuff discussed in each of those 2 lessons, lesson 12 and lesson 13, the end of lesson 12 and lesson 13, really were just reiterating each other. So what we just covered in lesson 13 is also the same stuff was covered at the end of lesson 12. So that's why I'm just going to do it all as lesson 13 right here. Okay. That way everything's kind of one place, but just remember you can look back to lesson 12 for some information. There might be some formulas or an explanation there that helps you kind of remember and solidify this information. Okay, so binomial distribution is a special case of a discrete probability distribution. Okay, so discrete variables, remember, are counting numbers. Okay, binomial, kind of the name kind of lends itself, bi meaning two. Okay, so binomial distributions have only two outcomes. So our outcomes are a binomial choice. And you can think of this as yes, no, true, false, right or wrong, heads or tails, pass, no pass, on time or late, on time or not, okay, etc. Anything with two options. Okay, and so when we're figuring out this probability, this is when the first lesson where we started using our graphing calculators to find probabilities. Okay, so what we used in our graphing calculator is, remember, we used second vars. Everything for this unit is under second vars because that's where all the probability is. And then we chose a binom something df. Okay, and what we put in here, well, let's talk about binom PDF first. And remember, this is where we started. We learned two different ones, binom PDF and binom CDF. So I'm going to cover binom PDF first. Binom PDF, what we put in is the number of trials, and we put in the probability of success, and then we put in the number of successes we're interested in. All right, and for your calculator purposes, what this is N, P, and X. Okay, so number of trials, remember, is, let's say I'm going to flip a coin 6 times, and I want to know the probability of getting so many successes. Okay, let's let that be our first example. Okay, and for these, by the way, I should add that I will tell you if it's a binomial distribution. Okay, I'm not assuming that you'll be able to recognize it. Sometimes you will. If you think about it, you'll say, oh yeah, that's right. It's asking me about right or wrong. It's a binomial. But I don't want you to have to guess and then get it wrong. I want to test you on your ability to answer the questions about binomial distributions. So I will always tell you it is a binomial distribution. It's a normal distribution. It's a discrete probability distribution. I will tell you those things, okay? So let's say I have a binomial distribution of flipping a coin, let's say 12 times, okay? And so we know for flipping a coin, we know the probability of getting a heads, you know, that's 0.5. And so let's say I should actually also add that I'm talking about flipping a fair coin, because that means it really is a 50-50 chance. If it's not a fair coin, then that means one side is weighted to give a different probability. But we're gonna talk about a fair coin. Okay, so in this case, my probability of success is 50%. Okay, so let's do this is, I think we're on example 2. I forget. Okay, but let's find the probability of exactly 6 successes. Okay, so now I need to figure out these values in order to put this in my calculator. Okay, I know what I'm going to put in is I'm going to put in a binom PDF, and I'm making this a big P to indicate, remember, this big P is talking about exactly X successes. Okay, and that's the difference between the two. The P means you're looking at exactly a certain number of successes. So I need to figure out what's my N, what's my P, okay, and what's my X. So for this one, I'm flipping a fair coin 12 times. This tells me my number of trials. That means I have 12 trials. And the problem you have on the test of the review might say a binomial distribution with 12 trials. Okay, so because I have 12 trials, that tells me N equals 12. My probability of success is 50%. This tells me that P equals 0.50. Okay, now I'm looking for exactly 6 successes. And this is how many successes I'm interested in. So that tells me X equals 6. Okay, so what I'm going to put into my calculator is binom PDF NPX. I'm going to put them in exactly that order. So N is 12, comma 0.5, comma 6. Okay. Oh, and I forgot to add, some of you, if you have an older calculator, this might be a 0, remember. So we're going to put this in our calculator. Second bars, binom PDF is A. So I'm going to arrow down. Now, this calculator that I'm using on my iPad only has the important things. To get it to yours, it's usually easier to arrow up. Okay, because notice I jumped from 3 to A. I'm skipping 4 through 0. Okay, and I'm going to press enter. And some of you, again, might have an arrow here or might have a list here, but we don't have that luxury. So let's bring this over here and remind ourselves, here it is, binom PDF 12.5 and 6, 12, comma, 0.5, comma, 6, and press enter. So that is 0.226. Okay, so if I flip a coin, 12 times, the probability of getting exactly 6 heads. And notice I didn't tell you which one was a success. My bad. I meant to say heads. Sorry about that. Okay. All right, so that's how we do the binom PDF. Binom PDF is when you're looking for exactly a specific output. Okay, and what's nice, remember, let's say you wanted to find the probability of exactly 2 successes. Is remember, you can use second enter to bring it back, and then the only thing you have to do is change the 6 to a 2. Okay, now let's say that what we wanted to find was the probability of 6 or fewer successes. And I'm going to put this here. By successes, I mean heads, although it's 50-50, so it actually doesn't matter in this instance, but let's be thorough about it. Okay, now 6 or fewer. Remember this binom PDF, I can only put in exactly 6 successes. So I have a couple options. I could do this the long way and find the probability of 0, 1, 2, 3, 4, 5, and 6 successes. So I'll repeat the same thing 7 times. I don't know about you, I'm way too lazy to be doing that. Okay, so that's why we talk about this cumulative probability. So what this really means is we're finding the probability of 0 or 1 or 2 or 3 or 4 or 5 or 6. Okay, so if we look at our probability distribution, what that might look like is this. Okay, so what the distribution is going to look like is each of these values represents number of heads that I get after flipping when flipping a coin 12 times. Okay, so just to be clear, what this means is when I'm looking at this 0 here, that means out of the 12 times, I get none are heads. And on the opposite end of the spectrum, this 12 means that all of them are heads. And it turns out what the distribution of this looks like is here. Okay, so this is my distribution of all those coin flips. Okay, so when I'm looking for the probability of getting 6 or fewer successes, what I'm talking about is 6 successes, 5, 4, 3, 2, 1, or no successes. So I'm looking for all of these probabilities here. So that's why, remember, I can add all these up, okay, but it's easier to tell the calculator to find 6 or fewer, and that's where my cumulative probability comes into play. Okay, and now we start using the binom CDF. Okay, where everything is the same, I'm still going to do N, P, and X. Okay, but now with this cumulative probability, what this X means, whatever value I put here, it's finding the probability of being here or fewer. Okay, so this number here is always included. This means whatever number you put here or fewer. Okay, so what I want to put in there, because I'm looking at 6 or fewer, I'm going to put in a 6 because I want to include that 6. Now everything else is the same. N is 12, P is 0.5, and X is 6. And notice what I have here inside my calculator is exactly the same information, because up here in part A, I was looking for exactly 6 successes. And down here, I'm looking for 6 or fewer successes. Okay, the only difference is in part B, I'm looking for a cumulative probability, and in part A, I was looking at just the exact probability. Okay, so the P is only 6 if I have a P, and the C is 6 or fewer. Okay, so we can put this into our calculator in a second vars, and binom CDF is directly below binom PDF. Press enter, and we're going to put in that same stuff again, 12, 0.5, 6, and there we get 0.613. Okay, and that makes sense because if you look at this, you look at this distribution here. Here I've got the middle, half is above, half is below, but I'm including this, so it's a little more than 50%. And that makes sense. You know enough now about what we learned with the normal curves and the empirical rule. You can ballpark it. That looks like a little more than half, yeah? Hopefully you see that. Okay, so now let's do one more. We did exactly 6 successes, then we did 6 or fewer successes. What if we wanted to find the probability of more than 6 successes? Okay, now in order to find the probability of more than 6 successes, we actually don't have a calculator option for this. Okay, so for this one, more than 6, remember these are discrete variables, and we're counting numbers. So if we're doing more than 6, that means we're looking at 7 successes, right? This means 6 is not included, so it's 7 or more. So what we're looking at here is we're looking at the probability of 7 or more. Okay, and you'll see combined, I'm looking, okay, for part C, I'm looking for that green box. In part B, what I found was this blue box. And you see combined, I have everything here. Okay, so in order to find the probability of more than any number of successes for a binomial probability only. Now remember, this is just binomial probabilities. What we need to do is we need to use the complement. That's the only way we can figure this out. Okay, so we found the probability of 6 or fewer. To find the probability of 7 or more, this is 1 minus the probability of 6 or fewer. So that's 1 minus 0.613. So that's 0.387. You can also think of this in terms of percentages. Okay, this means 100% minus the 61.3% we found above. So you can even just ballpark that, 100% minus 60% is a little less than 40%. And that's about what we found. This is close to 40%. Okay, so that's just another way to think about it. All right, so that's binomial distribution. Let me just mention a few other ways we could indicate this. Okay, if we're doing 6 or fewer, I just want to point out there's a few other ways we could state this. Okay, 6 or fewer, we could say 6 or fewer. We could say at most 6. We could say less than 7. Okay, these all three mean the same thing. Less than, because we're talking about discrete variables, less than means you got to kick it down to 6. Okay, if we're doing more than 6 successes, and another way we could look at this is 7 or more than 6, or at least 7. Okay, those are the 3 ways we could look at this inequality. Okay, so with that, let's move on to lesson 14. And I just want to remind you that everything I'm showing you here is summarized in all of the class worksheets. Okay, none of this information I've presented here in this video is new information. Okay, so if you're confused or want a little more information, you can go back to the source documents, the worksheets, and you can also go back to those lesson videos, the worksheet videos, or the class video for that matter. And I guess I should have mentioned, this earlier too. This document will also be on Canvas. Okay, so let's go on to lesson 14. This is where we started continuous probability distribution. And remember, continuous probability distribution is where we're going to be spending the rest of the semester. So if we were going to call any lesson we do, anything we do this semester important, it's really lessons 14 and 15. Okay, 14, 15, and 16 actually are probably the most important lessons of this entire semester. Okay, and they're the ones you'll probably use more often in your job or your major if you're using statistics. All right, so for continuous probability distributions, these are continuous variables. Before we were using counting numbers, now we're doing continuous variables, which are the variables we use to measure. Okay, examples of things we measure are time. And time is a weird one, but think about in terms of you're using a stopwatch. Okay, height, weight, length. Okay, those are examples of measuring things. Okay, and so now what we do is we're not looking at one and one. If it's more than one, it doesn't go to two because it could be 1.00001 or 1.0002. 1.0003. In between the numbers 1 and 2, there are an infinite number of numbers. Okay, so continuous variables, this is when we start looking at those curves, those what you might think of as normal curves. Okay, those types of distributions where everything is an arch of some kind. Okay, so, and another thing that's really interesting of this is when we're talking about the probability of x less than or equal to 15, the probability is actually equal to strictly less than 15. And that's kind of weird, okay? But the reason why is because, remember, just between 15 and 16, there's an infinite number of numbers. So if I tell you I'm looking for a number that's less than 15, I could look at 14.9 or 14.99. 14.99999, right? You see the point? Just in between 14.9 and 15 are also an infinite number of numbers. Okay, so removing that one value of exactly 15 doesn't make any difference at all. It is such a minuscule probability that we don't need to talk about them differently. Less than or equal to 15 means the same thing in this context as strictly less than 15. Okay, and I want to be clear, this is just probability we're talking about, okay? It's not always true that less than 15 is equal to less than or equal to 15. It's just if the probability, the probabilities are equal, okay? So we have different types of probability distributions, and in these distributions, area equals probability. Okay, and we like to shade in the area that we're finding to illustrate the probability that we're finding. Okay, but let's talk about these 4 different types of distributions. And when I'm drawing them, think about if you remember what we call these. Okay, give yourself a quick quiz. Okay, so here's the 4, and remember each of these peaks is a mean. Except in this one down here, we have a special circumstance where the mean and the median are equal. Okay, so what are each of these called? Well, this first one that we're looking at here has 2 peaks, and so we refer to this as bimodal. Okay, then these 2, this is where it gets a little bit tricky. Okay, you might remember that these are both skewed. But where a lot of students get into trouble is it's hard to remember, is it left skewed or is it right skewed? Here's the key. The skewing has to do with where that gentle slope lies. Okay, so in this one in the bottom left corner, the gentle slope lies on the right side, so we call this right skewed. And this one up here, the gentle slope is on the left side, so we call this one left skewed. Okay, now this one in the bottom right, this is our favorite one, and this is the one that we're really talking about in lessons 15 until the rest of the semester. This is normal symmetric. Okay, and most things we know about are normally distributed. Most of these common things, height, weight, length, if we're talking about one subject at a time, one breed of dog at a time, these things would be normally distributed. If we're talking about two different breeds of dogs at a time, we would wind up with a bimodal distribution. If, for example, we're looking at Chihuahuas versus Labs, that would definitely be a bimodal distribution. Chihuahuas tend to be very small, Labs tend to be very large. Okay, and here's an interesting way we can look at these curves here. I posted this on Facebook, on Canvas. Okay, so they asked a bunch of people. They asked them for each of these terms. Okay, they said, okay, put a percentage on each of these terms, and percentage from a assigned probability percentage. How likely do you think it is to happen if I give you this words from 0% to not at all likely, ranging all the way to 100% definitely going to happen, like the sun rising every day. Okay, and so it's just a really interesting graphic to look at this. And you notice here, there's these little bumps here. Some people said highly likely, only assigned it a probability of about 10–15%, which I found very surprising. And people highly unlikely assigned it a probability of 90%. I find that interesting. Okay, and I'd like to know a little more about that. I'm fascinated by these little bumps you see here. Outliers, yeah? Okay, so these curves are very practical and we see them all the time, okay? And we use them all the time to visualize data. Okay, in lesson 5, remember that data visualization, you really learned that all these many different ways we can visualize data. I just thought this was a really interesting way to look at it. And for what it's worth, they also did the same thing and looked at it with box plots. Okay, and you might remember box plots from lesson 5 or so. Okay, but where we're spending the bulk of the rest of the semester is in the normal distribution. And that's lessons 15 and on. Now, lesson 15 and 16, remember, are parts 1 and 2 of both normal distributions. But I'm going to keep them separated just because we did learn some new things. We learned one new thing in lesson 16. Okay, so here's part 1. And the main thing that we learned about in lesson 15 was the empirical rule. Okay, and what the empirical rule says is that the approximate area under the curve is based on the standard deviation. We can approximate the area. Okay, and this makes me realize we never talked about standard deviation. So let's back up, and I'm going to add that. Okay, well, standard deviation was actually something we talked about a little bit earlier in the previous units. But we use the standard deviation here. Remember, standard deviation is a way to gauge how spread out data is. Okay, so in lesson 15, we learned about the empirical rule, and that is that we can approximate data by using the standard deviation. Or I'm sorry, I misspoke. We can approximate the area under the curve. Okay, and what this looks like, here's a normal curve. It's hard to draw normal curves. There we go. Okay, this number here is the mean. Okay, and remember we learned about z-scores as well. That's part of the empirical rule, where z-score is 0 in the middle, and then we drew 3 tick marks on either side. Okay, so starting in the middle, let's switch these around. There's 0, that's my mean, and my median, remember. Oh, I don't know why I put a negative 1 there. Sorry about that. Okay, so starting in the middle, I'm going to go to the right. 1 standard deviation, 2 standard deviations, 3 standard deviations, and then going back to the middle and going to the left, -1, -2, -3. And remember, if you're not comfortable with the negative numbers, that's fine. Just go from the left, go 1, 2, 3, and just pop on negatives. And remember that the z-scores don't end here. Okay, it goes on forever. We just stop writing at positive and -3 because it's really unlikely to get values above 3. Okay, so we just stop out of laziness, to be perfectly frank. All right, so what the normal distribution tells us, what the empirical rule tells us is that within 1 standard deviation of the mean is 68% of the data. Okay, and by within 1 standard deviation, what we mean is in between -1 and 1. Okay, so here this is 68% of the data. Okay, and we also know that 95% of the data is within 2 standard deviations. So that's this here. Then finally, 99.7% of data is within 3 standard deviations. Okay, so that's the first part of the empirical rule. What we also get out of the empirical rule is how the term unusual is defined. Okay, so it also tells us that anything beyond 2 standard deviations is unusual. And that's beyond 2 standard deviations in any direction. Okay, so unusual is a technical standard, is a technical statistics term. So anything from here down is unusual, and anything from here up is unusual. Okay, so this is unusually low, or unusually cold, or unusually small, and this is unusually high, or unusually heavy, unusually hot, if you're talking about weather. And the reason why we get that too is because, remember, in between here, that complement area, and here, this is 95% of the data, which means the remaining is 2.5%. Okay, so it's not just 5%, it's 5% split in half. Okay, and that's why we say it's unusual, because if you're in this region for your height, let's say, you're only in 2% of the world, 2.5% of the world is with you on that height. Okay, so that's where the term unusual comes from. Okay, and remember, we use z-scores because z-scores are the normalizers. That's another term we have for them. I have these z-scores here. Okay, and the z-scores allow us to compare apples to oranges, okay, or SAT to ACT scores. It allows us to compare things that are completely unrelated to each other, okay, but it allows us to know, is this apple unusually large versus the watermelon, right? Hugely different weights of something, but if we can use the z-scores to determine if one of them is unusually underweight or unusually overweight for the category it's in, compared to the average apple weight or the average watermelon weight. Okay, and then another thing that we get from z-scores is that sign. The z-scores has 2 parts. Okay, the value tells us how many standard deviations of something is from the mean, and the sign, and by the sign I mean the plus or the minus, tells us if it's above or below. Well, I guess technically there's 3 parts, because while we're here, let's just say 2 or more standard deviations away from the mean is considered unusual. Okay, so now to find the probability of something, we have the empirical rule, and the empirical rule, I think the empirical rule was introduced in lesson 14. So let's make a note. Here's where all this information is on lesson 14. Okay, so I really should have added what we just did. That should be in lesson 14. It's not in 15. Okay, so I apologize for that. Okay, so let's make a note right here. This is actually in lesson 14. Okay, I'm sorry about that. But what we did get to in lesson 15 was using our calculator to calculate and determine probabilities. Everything I just talked about with normal distribution is actually in lesson 14. In lesson 15, this is where we started using our calculator to find the probabilities. Okay, so given a raw value, we wanted to find the probability of an area of certain thing happening. Okay, and remember, this is also in second vars. Everything for this test is on second vars. Okay, so if you're not sure what to do with your calculator, go to second vars and just hunt around and you'll find what it is you're looking for. Okay, so here we're using 2 normal CDFs. And it's normal because it's a normal distribution. And it's C, just like the C in the binomial, the C means cumulative. And what we're going to be putting in is the min, max, mean, and then the standard deviation. Okay, so for here, let's look at an example. Let's suppose I have a normal distribution with the mean of 60 and standard deviation of 5. Okay, and the first thing I'm going to be asked to do, let's leave that there, is let's fill in the normal curve. Then we're going to find the probability of something being between 50 and 60, the probability that something is less than 50, and the probability that something is bigger than 70. Okay, so here's my normal curve. Okay, first thing I want to do is I want to call out the standard deviation and the mean. So I'm told the mean is 60 and the standard deviation is 5. So that means the mean is 60 and sigma is 5. Okay, so the number I'm going to put in the middle here is 60. And then remember from here, I'm filling in the x values first. So I put an x over there to indicate I'm filling out x. Okay, and then remember I'm going to add 1 standard deviation. So my standard deviation is 5. So I'm adding 5 3 times, 1, 2, 3. Then I'm going to go back to the center and I'm going to subtract 5 3 times, 1, 2, 3. So I have 60, 65, 70, 75, back to the center of 60, and let's back up and we're going to subtract 5. So we have 55, 50, and 45. Okay, so those are my x values. I can also fill in my z-scores. Z-scores are always the same no matter what context you're talking about. Zeros in the middle, and we're going to do 1, 2, 3 to the right, because that's how many standard deviations we added to get to each of these values. We added 1, added 2, added 3, and then going back to the center, we subtracted 1, subtracted 2, subtracted 3. So we get -1, -2, -3. Okay. All right, so we filled in the normal curve. Let's now find the probability that x is in between 50 and 60. That's what this says. This says between 50 and 60. So I like to color in what I'm finding. I'm finding the area between 50 and 60. So that's there. Okay, that's the area I'm looking for. So what I'm going to put in my calculator is normal CDF. And remember, always write down what you're putting in your calculator, because you want to remember how you did something, especially if you make a mistake. You want to be able to find your mistake easily. And if you don't write down what you did, you're not going to be able to find your mistake. Okay, so the min leftmost number. Okay, so that's what this means, is the leftmost number, comma, rightmost number. And what's nice, when it's between 50 and 60, these numbers go into my calculator in the same order. So it's 50, 60, comma, mean is 60, comma, standard deviation is 5. And I'm just going to write down what we're going to put in our calculator, and we'll do all the calculations at once. And the reason why I'm going to do it that way is because, remember, we can just hit second enter and bring it back, and we just have to change these numbers here. Okay, now the probability of x being less than 50, what's that look like on my graph? That's less than 50, That's here. And remember, this doesn't stop at 45 and this doesn't stop at 75. They both keep going. It's just highly unlikely, so we just stop writing it. The values don't stop, we just stop writing it. Okay, so my minimum, my leftmost number, well, I don't know what this leftmost number is. I don't know how far this goes. But what I do know is if I pick a really, really small number, that'll suffice. Okay, so what I'm going to put into my calculator here is normal CDF. And I just do a negative and then a bunch of nines, like 5 nines is probably good. Okay. And then rightmost number or maximum is 50. And again, we have the mean 60, standard deviation is 5. Okay, so now more than 70. What does that look like? More than 70, here's 70. Here's 70, and I'm doing more than 70. Okay, so my minimum is 70. That's my leftmost number. My rightmost number, well, I don't know, again, don't know where it ends, so just pick a really big number. And I'm just going to do a bunch of nines. 2, 3, 4. I do about 5 nines usually. Okay, and again, then our mean is 60. Standard deviation is still 5. Okay, now let's put that into our calculator. Okay, second bars, normal CDF, enter. Let's do the first one. 50, comma, 60, comma, 60, comma, 5. Press enter, and we have 0.477, which makes sense because remember the empirical rule, everything left or right of the middle is 50%, and we have almost that. So 47.7% seems about right. Okay, always check to make sure, do a gut check to make sure your answers that you got seemed reasonable. Well, let's do the next one. Remember, I can just press second enter, and I can just change these values here. Negative, remember to use the minus. Don't use the minus button, you'll get an error. If you use this button, you see the difference in those two? You want to make sure to use the negative button. Okay, that's a really important thing. This is the #1 cause of errors. This should be the minus. Oh, whoops, not -1, just the minus. Negative, I'm sorry, I said minus, I meant negative. Okay, so we're going to press delete to get rid of that one. Okay, so we got -99999, comma, now I've got to change this one as well. Delete that. 50. No, there we go. 60 and 5. And we're good to go. Press enter, and what do we got? 0.023. Pretty darn small. And that makes sense because it's just that little bit of tail that we're finding. Okay, now the probability of 70. Second enter. Now, this one, I don't want to use that one. I'm going to bring back one of my earlier ones. So I'm going to press second enter one more time before I press anything else. That's a little trick. Okay, so I can go back here, change this 50, press delete, change that to a 7. This one, we actually want 99999. Oh, your calculator is going to operate just slightly differently. Your calculator, you can just write over it. Okay, my calculator doesn't work. I wanted to have these on the same page, so I'm using my iPad calculator so I can have these side by side for you. Okay, we're going to press enter, and we get 0.023. Again, notice those are the same probabilities. Let's look at this. Let's look at our graph. This is where our graph comes in handy. And do you see, this is from -2 standard deviations and down. This is from +2 standard deviations and up. So that makes sense that we would get the same values. Okay, the area is the same beyond 2 standard deviations. And also remember with the empirical rule, here's a fun fact for you. Okay, the empirical rule estimates this at each of these at 2.5%, which is 0.025. Okay, so the empirical rule is just an estimate, but you see it's a pretty good estimate. Yeah, that is lesson 15. Let's go into lesson 16. Okay, with the normal distributions, this is just a continuation. And remember, there wasn't a whole lot new in lesson 16. In fact, I think all of you thought it was pretty straightforward. Okay, well, not all of you, but most of you, many of you thought it was pretty straightforward. We just learned 2 new pieces of information in lesson 16. We learned how to change between Z and X using formulas. Okay, so to convert from X to Z, we use Z equals X minus the mean divided by the standard deviation. Okay, let's write this over here. X is your raw data value. This M is your mean. And remember, the sigma is your standard deviation. Also remember, in your calculator, with this one, the calculator is tricky. You have to put parentheses around the top because subtraction makes the order of operations be a little bit different. Okay, so in our calculator, you need to put a parentheses and then X minus M, close parentheses, and then divided by that standard deviation. Okay, if you wind up with a standard deviation, or excuse me, if you wind up with a z-score that's not too far off from the X score you started with, most likely you forgot the parentheses. That's why it's really important, anytime you're doing these, draw this normal curve, even if I don't ask you to. It helps you gauge. Okay, if I'm trying to find the z-score of, let's say, 52, or, okay, I know the numerical value should be somewhere between 1 and 2. You don't have to be good at negative numbers to be able to recognize that, okay? And I know it's hard to find, well, what is this as a negative numbers, and with the number line, it gets confusing, and that's fine. You don't have to know that, but just be able to recognize the numerical value should be somewhere between 1 and 2. If you wind up with a numerical value that's like 30, well, yes, it is possible to get a z-score that is 30. Totally possible, but not very likely, okay? And that's where this really comes in handy, because it gives you a really, really easy way to just check the value you get out of your calculator. In fact, if the test happens to be a multiple choice for that question, and there's only one value that has a numerical value between 1 and 2, pick that one. Okay, also, you know it's going to be negative. If you wind up with a positive value, you know there's a problem with that too. Okay, so it's always a good idea to draw this curve, even if you're not asked to, because it really helps you sort out and get a ballpark answer for what you expect. And that's just a good test taking technique. Okay, so going back to these conversion formulas, if we want to convert from Z to X, it's a little bit different. Now, those of you who took your algebra, you could actually, all we've done is we've solved this equation for X. Okay, so if you want to practice your algebra, by all means, you can try solving this on your own. Try solving this for X and see how much of your skills you remember. So we get X equals the mean plus the z-score times the standard deviation. And remember that z-score might be negative, so also remember for this one to use that negative, okay, that negative button, not the minus button. Okay, so that was the first thing we learned, was to change between X and Z. The next thing we learned was to find the X values given the probability or the percentile. Okay, right, so up above, what we were doing is we were given these X values and we were finding a probability. Okay, so and that's where we use normal CDF. Okay, I gave you X, you spat out, your calculator rather spat out a decimal probability. Okay, but we want to be able to go the other way around. Is I want to find the X value given the probability. Okay, so what that looks like is, let's suppose I have a normal curve here, and I've got my mean here, whatever value that mean is. And let's say I tell you that I want to find the value that goes with this here, and this is 0.20, or also known as the bottom 20%. Okay, I want to find out what X value that is. So the example, what the problem would state, let me write this down here. The problem would be something like, what X value is the cutoff for the bottom 20%? Okay, and what we use in our calculator to figure this out is right below normal CDF. What we're using is second VARs, because remember, everything for this lesson is second VARs, or not for this lesson, for this whole test, this unit is second VARs. And then we're going to use 3, inverse norm, INV NORM. And what this means is inverse norm, as in normal curve. And what we put in is we're going to put in the percentile associated with that. It has to be a percentile, and then the mean, and then the standard deviation. So do you notice that the order is just about the same, except instead of the min and the max, we're putting the percentile, and then still the mean and the standard deviation. So what I need to figure out for this problem is I need to figure out, I'm trying to find what X value goes with that bottom 20%. What's the cutoff for that bottom 20%? Notice I don't have enough information yet. Okay, I need to figure out what the mean is. But let's say for this example, the mean is, I don't know, 10, and the standard deviation is 2. Okay, so what we would put in our calculator then is we would put inverse norm, the percentile. Now remember, percentile is everything that lies below it. What percent is below? But as a decimal, always as a decimal. We only talk in percentages. We computate in decimals. Okay, and in this case, what's below is that 20%. So I'm going to put that 0.20. Then the mean, 10, and the standard deviation is 2. Okay, so put this in our calculator. Second VARs, and there you see inverse norm is right below normal CDF. It's number 3. Press enter. Percentile, 0.2, comma, 10, comma, 2. And press enter. And so that X value is 8.3, and just 1 decimal is fine. So for this example, knowing this mean is 10, the value here that marks that cutoff for the 20th percentile is 8.3. Okay, now I do want to point out, those of you with your fancy rechargeable calculators, okay, if you have a rechargeable, then what you would do is you would put the same information in, you would put this 20%, and you would choose left tail. And you see it's referring to this side here. That's my left tail. Okay, we're only ever going to be using left tail and right tail for this class. It also asks you center is one of those options. We're never going to use the center, only left or right tail. Okay, let's do another example. Okay, so let's do the top 20%. So what X value is the cutoff for the top 20%? Okay, now looking here for this top 20%, I'm looking for something like this. I'm trying to figure out what X value goes here, given that this is 20%. All right, so now this is where the calculator really gets different if you have that rechargeable version of the graphing calculator. Okay, we're going to do inverse norm. Remember, if you do not have that rechargeable calculator, you can only put percentiles into your calculator. Okay, so this top 20%, that isn't a 0.2 for the percentile. The percentile is everything that's below. Okay, so to figure out the percentile, it's whatever is the complement. I'm just going to recopy this here. Okay, so here's my, trying to find this value here. Here's 20%. So if that's 20%, what I need to put in my calculator is whatever this remainder is. Okay, so if I've got 20% there, does it make sense if I told you that this here is 80%? Oh, sorry, that's not a lot of contrast. Let's try that again. This is 80% here. Okay, so that's the 80th percentile. So what I would put in my calculator is not the 0.2, but the 0.8. And then continue and put the same mean and the same standard deviation. Okay, now you put that in your calculator. Okay, so I can just press second enter and it will bring back the one I just put in, and I can change that 0.2 to a 0.8 percenter. And so that value is 11.7. All right, now, those of you with a rechargeable calculator, you would choose right tail, okay? And then you would put in that 20% because you're telling it you want the top 20%, okay? Up here, you would also put in 20% in part A. You put in the 0.20. I'm sorry, not the 20% up, not the 20%, you'd put in 0.20. Because remember, we only speak in percentages. We computate and calculate in decimals. Okay, so this is one of those places where having that rechargeable calculator makes your life a little bit easier. So that's lesson 16. And then we have lesson 17, which is what we covered in class just a couple days ago. And that is the central limit theorem. And the central limit theorem, remember, this is a complicated subject. Basically, what you're looking for is the central limit theorem finds the probability of a sample looking a certain way. Okay, so just to remind you, to make this a little bit easier, is that when we were finding the probability of an individual meeting a certain criteria, weight or height, we use that normal CDF. That's lessons 14 through 16. Okay, so that's normal CDF, min, max, mean, and standard deviation. Okay, and the mean and the standard deviation are for the population given to you and will always be given to you. Okay, now note the mean might be a proportion or it might be a number, also known as a decimal or a percent or a proportion. Okay, now when we're finding the probability of a sample, that's when we're going to use the central limit theorem. Okay, so that central limit theorem adjusts depending on our sample size. Okay, and so that's where we use that standard error, or rather, we can't use the standard deviation anymore. Okay, we have to use the standard error. And remember that standard error is the standard deviation specific to that sample. Okay, so what we're going to use up here, we're still going to use that normal CDF. The only thing that's going to vary is instead of the standard deviation, we're going to put something that's a little, that's been adjusted for our sample. And remember, it's called a standard error because our samples are always going to differ from the population. Okay, so it's just called error just to indicate that it's talking about a sample, not a population. Okay, so that standard error is going to change depending on what we're talking about. Okay, so for means, okay, as in the average weight of a bunny, or mean or average weight of the bunny, okay, that is the standard deviation for the population divided by the square root of the sample size, okay, where this is the population standard deviation and n is the sample size. Okay, so this means what we're going to put in our calculator is normal CDF and still min, max, and the mean, except now instead of the standard deviation, what we're going to put is the standard deviation divided by the square root of n. Okay, and this square root button, you can find it as second x squared. Okay, so let me pull up the calculator. So the square root button is, see, here's the x squared button. Okay, I'm going to clear that. All right, so to get the square root, it's in blue, so I'm going to press second x squared, and that gives me that square root button. Okay, so what that means is every time our sample size changes, our standard error is going to change as well. Okay, and we can just put all that into the calculator at the same time. And then for proportions, an example of the proportions would be the percentage of bunnies that are brown. What we're going to put in our calculator is the square root of p times 1 minus p all over n. Okay, this is what the formula says, but now what the p is the population proportion. So that is to say, what percentage of bunnies are brown in the entire forest? And n is our sample size again. Okay, so notice what's happening up here in the numerator in the top. What we're doing is we're taking the population proportion and we're multiplying it by the complement. That 1 minus p is the complement. If 20% of the bunnies are brown, the complement is going to be 80%. Okay, so these two decimals should always add to 1. Okay, that's how, but you don't have to worry about doing that math because we can put it all in our calculator together. Okay, so what we're going to put in our calculator, and again, we can put it all in at the same time. We're going to do normal CDF, min, max, mean, and then second x squared, and that will give you the square root. Okay, it'll give you this part, but you need to be very careful. What we have to do is we have to worry about these parentheses. We need to add these parentheses in. Okay, so you need to make sure when you're putting this in your calculator, you need to be adding these 4 parentheses. So you're going to add this parentheses, and then you're going to put in the p, and then you're going to add close parentheses, and then you're going to add an open parentheses, and then you're going to do 1 minus p, and then you're going to close the parentheses. Then you're going to do it divided by, and then you're going to put an n, and then we can hit enter. Okay? If you would like, what you could do is you could calculate this all first and then enter that whole value just calculate this separately and then put it into the normal CDF. So let's do a couple of examples. Let's do an example of each one of these. So if I have, let's say the average weight of the bunnies is 6.2 pounds. What's the probability that a sample, and I'm always going to be told the sample size because remember, I have to use the sample size to calculate this standard error. Okay, so what's the probability that a sample of 105 bunnies weighs less than 6 pounds? Okay, so first of all, I need to figure out which scenario I'm in. Am I looking at a proportion or am I looking at a mean? Right, that's the real key here. Means mean I'm using this formula, and proportions means I'm using this formula. Okay, so here's the key. If you're given a percentage, you know it's a proportion. That's really the key, is here you're given a percentage. Okay, and then up above for the means, you're just given a value. You're told that the average weight of something, that's the key, is you're going to be told the mean weight of something. Probably you'll be told the mean. Oh, I guess I highlighted that already. Okay. All right, so this one I'm told that the average, I'm told that the average weight of bunnies is 6 pounds. Okay, so that's not a percentage, which means I'm going to be using the means. So what I'm going to put in my calculator, less than 6 pounds, okay, which means I'm finding the probability that X is less than or equal to 6. So what I'm going to be putting in my calculator is normal CDF. Remember, what I put in my calculator is min, max, mean, and now standard error, not standard deviation. Okay, so my min is less than 6, which means my min is negative 99999, and my max is 6. Mean, 6.2 pounds. Standard error, I'm doing average weight. I'm doing means. So I'm looking at this one here. That's the standard deviation divided by the square root of the sample size. Okay. Oh, I forgot to tell you the standard deviation. I forget what it was. Let's say it's whoops. I don't know, 1.2. Okay. So what I'm going to put here then for my standard deviation, I got to put in my standard error. So that's going to be 1.2 divided by the square root of 105. Okay, so let's put that in our calculator. Okay, so what I'm putting in my calculator is second bars, normal CDF. Oh, whoops. See how I have that square root there? That's why I like to clear the screen before I start. Okay, there we are. Second bars, normal CDF is number 2, negative 99999, comma 6, comma 6.2, comma 1.2 divided by the square root, remember that's second x squared, 105. Okay, so you see I don't have to figure out the value beforehand. I can just press enter. And there we have it. Our probability is 0.04. Not very likely. That's less. The average is 6.2 pounds, a sample of 105, having an average weight of less than 6 pounds is very unlikely. And what I should have said here, I apologize, I should say that a sample of 105 bunnies has an average weight of less than 6 pounds. All right, so the other option of what this could look like is, let's say that, so we have 20% of all bunnies are brown. Find the probability that a sample of 105 bunnies has over 30% brown bunnies. Okay, so I'm given a percentage. That's my indication that what I'm talking about is a proportion. Okay, so that means I'm going to be using the square root of p times 1 minus p divided by n. And I'm going to calculate this out separately just because I'm way less likely to make a mistake here. Okay, so this here, 20% of all the bunnies are brown, which tells me that p equals 0.20. Okay, so I have the square root of 0.20 times 1 minus 0.20 all over my sample, which is 105. Okay, now remember how we put this in our calculator. We have to be very careful. I've got to put parentheses around the 0.2 and parentheses around the 1 minus 0.2. Okay, and you might know that 1 minus 0.2 is 0.8, and that's fine. You can put in the 0.8, obviously. Okay, but I'm just using easy numbers here because it just makes it a little bit easier because I'm making these up as I go along. Okay, the subtraction isn't always as straightforward. So what we're going to put in our calculator is second x squared, and then you want to put those parentheses, and then the 0.2, close those parentheses, open up a new set, 1 minus 0.2, close those parentheses, divided by 105, and then press enter. Okay, didn't crash again. Okay, so clear screen. I always like to start with a cleared screen because of what just happened earlier. Okay, so second x squared open parentheses, 0.2, close them, open a new set, 1 minus 0.2, close them, divided by 105. Press enter, and there we have it. So this value here is 0.039 is our standard error. Now we can go about finding the probability. Okay, and we're finding the probability that over 30%, bring this back, yeah. So we're finding the probability that over 30% are brown. Okay, so what that means is what we're going to be putting in our calculator now. So this is 30% and above. So what we have is normal CDF. And remember, it's still, we're looking at min, max, mean, and our standard error now. Okay, so our min is 0.3 because it's a percentage. We only talk in percentages. We never compute in percentages. So I have to switch that to a 0.30. Okay, and the max, 99999. And again, you might recognize that it can't be over 100%, but remember, I like to use the numbers that work 100% of the time, and that's 9999999. And that way we don't have to worry about the context. Just use the 99999. It works every time. Okay. And then our mean is 0.2, and our standard error we can put in that 0.039. So now let's go to our calculator. Clear. Second bars, normal CDF, 0.3, 99999, 0.2, 0.039. Enter. There we go. 0.005. Highly unlikely to have a sample of over 30%. Okay, that's less than 1%. All right. So there you have it. That's your overview. I will post this document that I just made on Canvas under the Unit 2 module, Unit 2 test module. Okay. Hopefully that answers some of your questions. And remember, always get in touch if you have further questions. Okay. Good luck on the test. I'm sure you'll do great.